is exponentially more. I hope it speeds up because I'm tired of this movie. Once we hit spring break, it's a slippery slope to not try. I think I'm already there. We're barely keeping our balance. It's like one of those like, slides where you go down on the mat and you're just like,
All right. Here we go. So today we are talking about pretty much a lab, kind of revealing all things that were hidden. So describe magnetic field, pattern around, how ferromagnetic materials become magnetized, some magnets are stronger than others, how magnetic poles of the earth are oriented, describing the why behind what you observed in there. Okay, so get out you might reference your lab. Okay, correct answer is B. Okay, goes out of north into south. So you should have guessed either B or C. Okay, here's the additional facts that you did not know. You observed from your lab out of north into south, outside the magnet. Magnetic field lines are complete loops. Okay, so in order to make a complete loop, you need to keep on going with that. So inside the magnet, not on the outside, but on the inside, magnetic field lines are going from south to north. The outside, you go out of north into south. Get that? So out of north into south, making complete loops. So inside the magnet, they go from south to north. Good there? So, distinction between electric charges and magnetic poles. Opposites attract, likes repel. Out of positive and negative. However, here's a really big distinction, probably the most popular. You can have a single proton. You can have a single positive charge. You cannot have a single north pole, so far that we have discovered. So a scientific term for that is magnets are all dipoles. There's two of them. You cannot have a monopole. Okay. Have a conversation.
No.
Okay. Correct answer by process of elimination is D, domesticated dingo. Okay. So your three ferromagnetic elements are iron, nickel, and cobalt. Iron, nickel, and cobalt. Okay. So anything that sticks to a magnet has to have one of those three, at least one of those three elements: iron, cobalt, and nickel. Okay. The most popular substance that we interact with metal-wise is steel, which has iron in it. Okay. The ferric, that's, I think, Latin for iron. That's where that gets its symbol from. So like ferromagnetic stuff made of iron. So why these three? I think they covered this in honors, but not in regular. You have your 1s orbital, your 2s orbital, and then your d orbital, right? Or p orbital. Okay. And you would kind of like tally electrons by this methodology. Okay. These arrows represent the spin, electron spin. One's usually up, down. And then, like, they're going in opposite directions. The spinning electron actually creates an magnetic field. But because they spin in opposite directions, they cancel those two magnetic fields cancel each other out. Okay. That's usually how it works. But these three, for reasons beyond this class, their valence electrons are unpaired in their spin. They're not counterbalanced. And so their atoms have a net magnetic field. And that's what enables them to interact with magnets and to become magnets. Okay. You heard that? So iron, nickel, and cobalt are your three things that react to magnets. Okay, so here we've got D, ferromagnetic elements, which attract are these things, but which ones repel? Have a conversation. The answer is? The answer is E. Educated elephants. So, hopefully you saw this in your lab. If you had a rubbed nail and an unrubbed nail, this would attract either way, however you tilted that. Okay with that? But if you had two rubbed nails, one would repel, the other side would attract. The only time you get repulsion is if you have two like poles coming near each other. All right with that? Okay. So these ferromagnetic elements within their, like in a compound or something, they will make, as the atoms come together, their crystal lattice makes little crystals called domains. And those domains have a magnetic orientation. So if you pulled a piece of iron out of the ground, all those crystals are scrambled in terms of which way their magnetic field is pointing. But if you take that piece of iron and you place it in an external magnetic field, either that's strong enough or you leave it there for a long enough period of time, those crystals, some of those crystals will actually start to shift, pivot, and align themselves in the same direction as the external magnetic field. If you leave it there long enough and it's strong enough, you can actually cause most all of them to shift their orientation. And this is where a permanent magnet comes into play. All that. So, just to give you an idea of the size of these magnetic crystals, they're somewhere on the order close to the same size as a red blood cell. So, like paramecium, 60 micrometers. So, like paramecium, you saw that in your class, biology class. It would probably take up this whole screen. Just to give you like, so they're microscopic, but not that crazy microscopic. Like a middle school microscope you'd be able to see them. For that. Tell your neighbor. Correct answer is, got one vote for A, B, got some A's and B's. All right. Correct answer is B. The reason why, here's two reasons. Number one, this is going to end up sticking to, like if you let it touch, it would stick to the magnet. Okay. If this was another north, then it would tend to repel. Here's why this is actually comes south. So the magnetic field of the bar magnet is going out of north into south. Out of north into south. The magnetic field, the external magnetic field, is causing some of those crystals in the nail to align. So inside the magnet, inside the material, magnetic field lines go from south to north, from south to north, and then outside it goes out of north into south. You all right with that? You might want to reference your lab on this one. Tell your neighbor what you think. This is solely based upon your observations from the lab. I don't know how you'd answer that otherwise. Yeah. Correct answer is B. B. Okay. Here's how you figure it out. Here's what goes on to make this thing. Okay. So initially, those domains, those magnetic crystals, we're going to say cannot travel, can't migrate, can't move through, but they can rotate. They can pivot. You okay with that? So, initially, the south poles of these domains are like attracted to this. But as you drag this across, those south poles are like and they end up lying down. Does that make sense? So you drag those across, and as you do that, I'm going to make these huge so you can actually read them. As you drag it across, the south poles end up laying down, so that this side is the south pole, and this side is the north pole. Does that make sense mechanically, physically, what's going on there? Okay, here's the memorized. This is in my brain. I mean, you can put it out in your brain however you want to. Wherever you end up, it has the opposite pole of your magnet. Wherever you end up, that has the opposite pole of your magnet. Good with that? So try that newfound knowledge out on this. have a conversation.
Oh,
Correct answer is dangerous dinosaurs. So as you drag this across, this side becomes north, so that's south. As you drag this across, this becomes south, so this becomes north. As you drag this across, this becomes north. As you drag that across, that becomes south, making that north. Making sense? You can do it on your own. Okay. Here we go, C. Okay. This will continue to occur until you get down to trying to split an atom. Good with that? Okay. So, popular question comes, well, how do you make a really strong magnet? Like, that's a cool thing, right? Okay. Ultimately, what you're going for is to increase the magnetic field, make the magnetic field stronger. Each one of these would have that cause. All of those, like E is the correct answer. So as you have a bigger magnet, there's more domains contributing to the net or the total magnetic field. So if you have a material, a certain material, and you have a bigger piece than another piece that are magnetized, the bigger piece is going to have a stronger magnetic field. Okay. The second way is you're going to have a higher percentage of domains going in the same direction. So the bar magnets that we used in class are actually really weak magnets, okay? Because not a high percentage of their domains are going in the same direction. That's why when at the beginning I gave that disclaimer, like, hey, when things attract, they'll attract, but when they repel, they don't really do that great. I don't know if anybody got their magnets to stick north on north. That's because not a high percentage of them were going in the same direction. Okay. This would be a much stronger magnet than that. Okay. And then the third way is if you have chemical characteristics that you have a lot of domains densely packed in there. If you have ever heard of like a super magnet, or neodymium magnet, rare earth magnet. Those are all the same thing. They're just really strong magnets. They look silver, like chrome. That's actually the casing. If you break those open, they actually look like a dark gray ceramic type material. But they have their domains are really packed in there, so they're really strong for their size. So anything that would cause the domains to become more randomized it, is going to make it tend towards demagnetized. Okay. But one way to do it is to drop it. I just made that magnet weaker than this magnet simply by dropping it, causing it some of those crystals to begin disoriented, misaligned. Okay. You can also heat it up, cause the vibrations. Okay. Cutting it in two is not going to change the magnetization. It will cause you now have two smaller magnets that are weaker than the whole because, well, the half magnet is weaker than the whole magnet just because of the size, but it's still magnetized. Okay. So B and C cause it to become demagnetized. Sorry. B and C cause it to be demagnetized. Ran out of batteries. All right, so let us talk about the lab on page 1. It asked, which magnetic pole of the Earth does the northern tip of the magnetic compass seek? If you just answer that nonchalantly, you either got it wrong or you put down the right answer, but you didn't engage with your brain. That should have invoked a what? That doesn't make sense. If it didn't invoke that, you either got it wrong or you weren't paying attention. You're just like, okay, that's what it says. Because so compasses point which way? North. That's why we use a compass. Okay. But in the lab, you found that magnetically it points south. Okay. That's where the what should come from. Okay. Here's the answer. Where Santa Claus lives, the North Pole is the magnetic South Pole of the Earth. The geographic North Pole is the magnetic South Pole.
What you said, the geographic North Pole?
The geographic North Pole, where Santa Claus lives, is the magnetic South Pole. So, this is one of those weird things. But the explanation is better than Ben Franklin just guessed wrong. Okay, here's where this came to be. Chinese were the first people to discover magnets. They were naturally occurring chunks of iron called lodestones, and that they found if you placed it on a piece of bark and you floated it in the water, it would orientate itself towards the North Pole, towards the north. Okay, this was a huge technology breakthrough. Because before that, when you sailed ships, you at night specifically, you would use the stars to navigate. But if it was a cloudy night, you were stuck until the morning where the sun came up in the east. But now with this compass, so a compass is just a magnet that's able to pivot. I mean, you made a compass, right? By magnetizing the nail. Okay. So if you are a salesperson selling this compass, what would you call this? Hey, check this out. This thing points north. This tip right here points towards the north. Points to the North Pole. It goes to the North Pole. It goes to the north. This is, what do you think we're going to call that? Well, this is the North Pole. This is South Pole. Right? I mean, makes sense. No one ever thought, like, hey, what if we took two compasses and brought them next to each other? Like, why would I need two compasses? I got one for my ship. I don't need two. It wasn't until we started playing around with it and doing some experiments. They're like, oh, wait a minute. This is just a magnet in the Earth's magnetic field, and opposites attract and likes. So this North Pole seeks the geographic North Pole, but has to be, by magnetism, the magnetic South Pole. So there's a distinction between the North. Sorry, you got to watch the adjective. Is it the magnetic pole I'm talking about, or the geographic pole I'm talking about? Got that? Okay. So turns out that the magnetic pole is a little bit off of the geographic pole. If you ever take an orienteering class, oh yeah, we've got tons of time. Looking at the clock, going, oh my goodness, we're running out of time. We got tons of time. We're on a period. Yeah. All right. So if you ever take an orienteering class, there's this idea of like magnetic north and true north. So that magnetic north is actually shifting over time. So make sure your map, if you ever do these like compass courses, are up to date, where it's actually shifting kind of rapidly nowadays. And this is due, so the magnetic field we think is due to the convection currents in the center of the Earth. There's a lot of molten iron in there that's creating this magnetic field. And those convection currents are changing. But that's not the weirdest part. Every once in a while, the magnetic field, the magnetic poles flip. We think it's just due to different convection currents, but like if we look through the geological layers and we look at like how iron is arranged magnetically, the black bands show us like how it's arranged now. The white bands show us how like the poles are flipped. And so like flip-flops, this is a picture of the transitionary flipping process. So people always ask like, when's the next time this is gonna happen? We don't know. I mean, look at this. There's not really a set pattern there. What would happen if it happened like tomorrow? It would affect some stuff. It wouldn't be like, I think the biggest thing would be we wouldn't be as protected from the sun's rays. It wouldn't be that good of a magnetic shield. That would probably be the most damaging effect. GPS would be off. Yeah.
Wait, so how long does it take for
it to flip?
Yeah.
That's a good question. I don't know. Probably like Like if you look at millions of years, probably like a year or two.
Would we know if it's flipping or when it's like just like once it finally flips?
We would know.
We know.
I mean, you want to feel it, but
No.
we could measure it. Yeah. It would be, it wouldn't change. The biggest thing would be the sun's rays would be more dangerous. Like cancer giving stuff.
Oh.
Yeah.
When was the last time it flipped? I can't see.
110
million years ago.
Yeah, it's long, like dinosaur age.
Oh, so it's been a long time.
It's been a long time.
Bound to happen there.
Why was it so frequent before?
Yeah, why
Alright,
What's the media changing?
I don't know. Maybe someone else does that studies this stuff. I don't know. That's a good question. Like, why is it stable here and not here?
Look right there.
Like, blah, 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 yeah, yeah. That'd be,
Maybe the dinosaurs then died because of an asteroid. Magnets got flipping everything.
maybe, I don't know. All right, last question. So you even pay attention to the adjectives of what poles we're talking about, geographic or magnetic.
It hurts my brain.
Geographic is
A question that they put not in there. So like you want to answer yes, but they just say you don't want to.
You don't know how to answer the question.
But like no, you really don't know yes. But
have a conversation.
South Pole.
Or when they say don't not answer the question.
yeah, like what is that? Not answer.
So that's that means answer the question.
So answer.
So is it north or is it south?
I think it's south.
I'm glad you got that answer.
You guys either A.
That's north.
Could be C.
No, I definitely think it can be.
Okay,
Maybe it's the answer.
ready?
Why don't you be like,
Okay. The magnetic South Pole is going to attract to the magnetic North Pole, which is located where? It's located in the geographic south. B.
Yeah, so if this,
Give us
so
that
if
marker
the
every
poles
time and be
flip
like,
when we're in like
alright.
college, all of this is just
After
wrong.
Or is it just
That's just opposite.
Wait, so then it would make sense.
Just
Yeah.
opposite.
Is it a pole?
But then the compasses would point south.
Wait, does that mean Santa
Never
has
mind.
to?
Maybe we'll be alive in a lifetime where the poles flip.
Honestly, our lifetime has had enough.
Enough crazy.
Does that mean
stuff.
scientists say we are overdue for a full flip?
What?
I would be like, this is finally predicted it.
Good question. All right.
Ever present.
Got a pre-quiz due on Wednesday.
I did not comment today. I thought it was good.